Okay, so let's take a look at another example. Um, that's the volume of a pyramid of height h and square base of size L. So what does that mean? You have a pyramid. Its height is h. So that's the vertical height. That's h. And the base, this base, is a square L by L square. We want to find the volume of this, a formula for the volume of this. Maybe you've already seen the formula for the volume of a pyramid, but what this new piece of knowledge coming from calculus teaches you is that you don't need to memorize this formula. Every time you need it, you can derive it. So that's what I'm going to do. So the best way to slice this pyramid is to, if I put the axis of the pyramid, what used to be the altitude, if I put it along the x-axis, then the base will look like a vertical to the x-axis. And then when I slice it vertically, every slice will be a square. It's just that as you go from this tip to this bottom, the slices get larger and larger. But all of them look like a square, which is good news. So here I show you a typical slice right over the point x. I have to figure out a of x. Remember, if I know a of x, the area of the cross section made at x, if I know that as a function of x, then all I have to do is to integrate that from 0 to h, and that's going to be the volume. So the cross section at x is a square of size, uh, I don't know, some L. The thing is, you should think of this capital H as a given number, which is the height of the pyramid. You should think of the capital L as a given number, which is the size of this base square. I don't know, like 10 and 7, whatever. And then, given this information, you should try to figure out what kind of square, what size square you get if you cut it above some x. And the answer will definitely depend on x. If x is very close to 0, that size is very small. If x is very close to the base, that size is nearly capital L. So whatever this little l is, this is like a function of x. It changes with x, with the property that if x is 0, this little l is 0. If x is uh, capital H, the little l will be big L. So how am I supposed to find little l? Look at the picture. Everything is proportional. So similar triangles, using similar triangles, you can see that everything changes proportionally. So using similar triangles, I can say that x over L must be the same as h over big L. This is by similar triangles in this picture, and therefore little l must be L over h times x. I don't like that box. That box looks horrible. Okay. So this is bisimilar triangles. So this proportion is fixed. X divided by L is the same as H divided by big L. Set up that proportion. This ratio is the same, so solve for L. L times H must be big L times X, and therefore L can be expressed in terms of X as this constant times X. Now, to check that this answer is correct, see that when X is 0, L is 0, which makes sense. If I cut here, the size of that square is 0 by 0. And when my X is H, namely when I cut it here, the size must be big L. So when X is H, that H cancels this H, and little l will be big L. So that checks. So that's the cross section at X is a square of size L, where L is this. And therefore, that allows me to find the formula for the cross-sectional area function. What is the area of a square of size L? L squared. And that's this squared, because it's a square of side little l. So its area is little l squared. And this is L squared over H squared times X squared. You should think of this as a fixed number. You should think of this ratio as a fixed number. The only thing changing here is X. So this is the formula for the cross-sectional area function. And according to what we learned, the volume would be the integral from 0 to h of a of x dx. If I integrate this, and this everywhere in this picture, x varies between 0 and h. That's the interval for x. So if I integrate this function from 0 to h, by this function I mean the cross-sectional area function, that should give me the volume. Since I have a formula for the cross-sectional area function, I can plug it in. L squared over h squared x squared dx. This is a simple integral in that I can take this constant and put it outside, and essentially I'm integrating x squared. So that's L squared over h squared. And then antiderivative of x squared is 1/3 x cubed, evaluated at h and then 0. And this will be h cubed. When I plug in h, I get h cubed over 3. When I plug in 0, I get 0, nothing. So it's h cubed over 3, h cubed on the top, h squared on the bottom. It leaves one h on the top. And what I get is 1/3 of L squared times h. That turns out to be the formula for the volume of this pyramid. How do you interpret this formula? It's very simple. If instead of a pyramid, if you had a box, just a regular shoebox with an L by L square base and height h, what would be the volume? Well, the volume would be the area of the base, which is L squared times h, right? The area of the base, L squared times h. This would be the volume of a box, of a rectangular box whose base is an L by L square and whose height is h. What this formula for the pyramid shows you is that the volume of the pyramid of the same size base, but now it's a pyramid. It's not a box. So it shrinks as it goes up. The area of the pyramid is a third of the area of the corresponding box because of this 1/3. So it's a third of the area. The area of this pyramid is a third of the area of the corresponding box. That's how you interpret the formula. Okay? I'll clean up this picture later, but I hope it's clear. Now, one class of, so really this idea that the volume is the integral of the cross-sectional area is the essential idea here. Now, you can, and I showed you two examples of this, you can apply this general idea, volume equals integral of a of x dx. You can apply this general idea to some special cases. One of those special cases is solids of revolution. These are solids that are obtained by taking some region in the plane, some axis in the plane, and revolving this region around this axis. Imagine that this is in three-dimensional space. You pick an axis, you take a piece of cardboard looking like this, and then you rotate this piece of cardboard around this axis. What you get is something like this. This is an example of a solid of revolution. A solid of revolution is a solid in space which is obtained by revolving some region around some axis. My claim is that the general principle that we learned, that the volume of a solid is the integral of its cross-sectional area, takes a very simple form in this special case. Not all solids are solids of revolution. For example, a pyramid is not a solid of revolution. Obviously, you can't get a pyramid with this sort of flat shape by revolving something around an axis. The cylinder is a solid of revolution. If you take this rectangle, you take this rectangle and you revolve it around this axis, you get this solid cylinder. Some solids can be obtained as a solid of revolution, some don't. Pyramid doesn't. A cylinder does. We'll see that the sphere does. Things that, I mean, some degree of roundness should be present in order to be able to get your solid by revolving. So my claim is that if you take the graph of a function f, let's assume this function is positive, so the graph is above the x-axis. If you take the region under this graph, that's this region, and if you revolve it around the x-axis to get the corresponding solid depicted here, you can easily find its volume by applying the general principle that the volume is the integral of the cross-sectional area. What would be the cross-sectional area in this case? If you cut above some x, because this solid is obtained by revolving, the cross-section will be just a round circle. It would be a round disk, as a matter of fact. That's why this is called the disk method. So A of x is the area, by definition, is the area of this cross-section made over x. This cross-section is a round disk. I mean, this is a perspective picture. Don't get confused that this looks like an ellipse. Well, it's supposed to be a round circle when you look at it, not directly, but at an angle. So this section will be a round disk. So in order to find its area, and that's A of x, all I have to do is to figure out its radius. But what is this radius? Remember where this comes from. This radius is the same as this height if I make it right above x. If I consider x, what is the length of this line? It's just f of x. This is f of x, right? So here, let me blow up the picture so I can write. So this radius is just f evaluated at x. F is the given function that we started with. Remember, we started with the graph of a function f. We took this region and we revolved it. We got this solid. In order to find its volume, I need to find its cross-sectional area function. So I pick some generic x between a and b. I cut the solid. Because this comes from revolving around the x-axis, the cross-section is a round disk, whose radius is just f of x. So what is the area of a round disk of radius f of x? It's just pi r squared. So it's pi times f of x squared. And this is true for every x between a and b. So there is a very simple formula for the cross-sectional area function if the solid comes from revolving the area under the graph of f. It's just pi f of x squared. And therefore, the volume of such solid of revolution is the integral of this guy, a of x, from a to b. Since pi is a constant, I can put the pi outside the integral. It's pi times integral from a to b of f of x squared dx. That's the formula for the volume if you apply the general principle that the volume is the integral of the cross-sectional area function. Okay? This is usually called the method of the disk method, or method of disks. Why? Because in this example, in this very special example of a solid of revolution, if this region right here, is leaning against the x-axis, which is the axis of rotation, after you rotate it, you get a solid of revolution whose cross-sections, every cross-section looks like a disk. And what you do in order to find the volume is you find the area of this disk, which is pi f of x squared, and then you integrate it from a to b. You should look at this formula. I'm not giving you different formulas. This formula is just a very special case. This formula is just a very special case of the general formula that we developed earlier. This is the most general formula. Volume is the integral of cross-sectional area. In the very special case where the volume is a solid of revolution, the volume reduces to this formula because your cross-sectional area function reduces to this formula. Let me show you an example, a couple of examples, and then maybe I'll stop. Volume of a cone of height h and base radius r. If you think about it, again, let me draw something. This is pretty much my scrap paper. If you have a cone of base radius r and height h, that's the cone. That's the cone of, it's a solid. The base is a circle of radius r, and the height is h. You can think of this cone as a solid of revolution. All you have to do is to take this triangle and revolve it around this axis. If you take this triangle and revolve it around this axis, obviously you get that cone. So the cone is a solid of revolution, and if I put it against the x-axis in the right position, I can apply the previous formula. So how about doing it this way? That triangle that I just showed you, I can put it like this. So that's the right triangle whose base is right, whose height is right here. So this is x equals 0 to x equals h. This length is h. And the radius is r, so I put it here. And then when I rotate it around the x-axis, of course, you get that cone. So this is exactly following the general pattern that I showed you here, except that it is this function, this linear function, whose graph I'm rotating. So I have to figure out, so this is like the graph of my f of x. I have to figure out which function has this graph. Well, that's a truly elementary question. Oh, in other words, I have to figure out the equation of this line. It's the straight line at height, at slope r over h, passing through the origin. So the formula for this is y equals f of x equals r over h times x. It's a linear function, right? This function, r over h, you should think of r and h as fixed numbers. R over h is just a number times x. So this is the straight line. This equation describes a straight line passing through the origin at slope r over h, which is consistent with rise over run. Okay, so in other words, the solid cone of height h and base radius r can be thought of as the solid obtained by revolving this region around the x-axis. And this region is the region underneath the graph of this f. So this is exactly the type of problem that I was talking about like 5 minutes ago in the previous slides. So in the previous slide. So I can say that the volume is pi times integral from 0 to h of f of x squared dx. And who's my f of x in this problem? This linear function. So that's pi integral from 0 to h of r squared over h squared x squared dx. I just took this f and I substituted that f here. I have to square it, so that's why everything is squared. This guy is a constant. I can park it in front. So that's pi r squared over h squared. Integral from 0 to h of x squared. Basically, I have to integrate this. So it's 1/3 x cubed evaluated at 0 and then h. This part of the computation is very similar to what we did for the pyramid. So this is pi r squared over h squared times 1/3 of h cubed. And h cubed and h squared, they simplify. It leaves an h on the top. So I can write this as 1/3 of pi r squared times h, which resembles the formula for the volume of the pyramid that we obtained. What this is saying is the again, if you want to interpret this, maybe I can just add a page here to show you. If you had a cylinder, oops, what is this doing? Oh, if I had a cylinder of base radius r and height h, we showed that the volume is pi r squared, the area of the base, times height. What this formula is, what we just derived for the cone, shows that if you consider a cone of the same base size, radius r, and the same height, so this cone is obviously has less volume than the corresponding cylinder. You have to do 1/3 of it. That's what this result says. So the volume of a cone, just like the pyramid, the relation between, remember the relation between the pyramid and the corresponding box? The pyramid had 1/3 of the volume of the box. There is a similar 1/3 relation between the volume of a cone and the volume of a cylinder of the same size. So these two are nearly identical in nature. Both of them have this factor 1/3 in front of them. As the last example, let me show you how to compute the volume of a sphere of radius r. You may have seen the formula for the volume of a sphere of some radius, but maybe this is the first time you actually see why that formula is correct. So I'm going to derive that formula for you, noting that the sphere of radius r can be thought of as a solid of revolution. Again, if I show you something in my makeshift scrap paper, if I take a half disk, imagine you make this half disk out of a piece of cardboard, and you lean it against this axis. This is a line in the space, and you rotate this this piece of cardboard, the semi-disk, around this line. What you get is, of course, a sphere. It's not hard to imagine that rotating this half disk around this line will generate a solid sphere. Think about it. It's not really difficult to imagine. So if I want to find the volume of a sphere of radius r, what I can do is, let me get rid of this. What I can do is pick this half disk of radius r, put it against the axis of rotation, which is supposed to be the x-axis here, and then rotate it. But this region, this half disk, is the region under this graph. If only I could find the formula for this graph, then that would be my f of x, and then I could use the formula for the volume of a solid of revolution using this so-called disk method. So it all boils down to finding the formula for this semi-disk, and that's very easy, because if x squared plus y squared equals r squared is the equation of the circle of radius r centered at the origin, if I solve this for y, I get two solutions. Y squared is r squared minus x squared. So y is plus minus square root of r squared minus x squared. I take the plus sign because this is the upper semicircle. If I take a negative sign here, if I put a negative sign here, that would describe the lower semicircle. So this is the equation of the upper semicircle. So my f of x is just the square root of r squared minus x squared. That function, of course, x is here between negative r and r. That's the domain. So this function has its graph as this semicircle of radius r centered at the origin. So that's my f. I take the region underneath between the graph of f and the x-axis. I revolve it around the x-axis. I get the solid sphere of radius r. As such, the volume as a solid of revolution, the volume should be given by the formula, pi integral from negative r to plus r of f of x squared. But what is f of x squared? We're lucky because f has this square root in it, but my formula has a power 2 in it. So when I square my f, I get rid of that radical, and things will simplify. So that's a good coincidence. That's pi. Let me write it here. Let me continue this here. That's pi integral from negative r to plus r. F of x squared is just r squared minus x squared dx. Again, you can think of this as, since this is an even function and I'm integrating over a symmetric interval, this is twice the integral from 0 to r of r squared minus x squared. You should think of capital R as a fixed number given to you. The only variable is x. So that's twice r squared x. I'm taking the antiderivative of r squared, and then antiderivative of x squared is 1/3 x cubed. Evaluated at r, then 0. So at 0, you get nothing. When you plug in r for x, you get r cubed minus 1/3 of r cubed I'm sorry, here I have an extra pi in front of the whole thing, which I missed. So here I must replace this with 2 pi, and here 2 pi. So I have 2 pi. I have a pi coming from the pi that I had here, which comes from the formula. And I have this 2 because instead of integrating my even function from negative r to plus r, I said that's twice the integral from 0 to r. Sorry about that. So I had missed a pi here. So 2 pi r squared x minus 1/3 x cubed. So now I plug in r. I get r cubed minus 1/3 of r cubed. That's 2/3 of r cubed times 2 pi. That's 4 pi over 3 r cubed. At 0, I get nothing, so I don't bother with that. That's the final answer, and it is the well-known formula for the volume of a solid sphere of radius capital R. It's 4 pi over 3 times r cubed. Okay, this is enough as far as this lecture goes. Again, this lecture is what was supposed to be the lecture on yesterday, on March 16th. I will record the next lecture, which is the substitute for the Thursday lecture. I will record it as soon as I get a chance, and I will post it on Google Classroom. So I'll see you soon. Take care, guys. Stay safe.